Today we have a six-term expression with the confusing instruction simplify. Can mean a lot of things. In this case, though, it's almost certain that we'd have to start out by factoring this expression. Now, the greatest common factor is easier to identify than you might think. Again, this is six cubed integers, the sum of six cubed integers. But notice that the GCF has 8218 raised to the 2739. And that's quantity cubed. Just writing it down, you probably can pick it right out, but just in case. This term right here, the greatest common factor, the highest common factor, is common to all of these terms. Now, this term contains a 20 cubed, a 5 cubed, a 4 cubed, a 3 cubed, and then over here you just have the same two cubes. Okay, but anyway, this is the greatest common factor, so we'll begin by factoring that out. And it's just what I said right here. We've got it right here. And so we're going to remove it, write it like this, and you can see just by looking up here, you have 20 cubed left from this first term. There's your 20 cubed. You have 5 cubed left from this term, and so on all the way out. So we did factor it into something that looks more palatable. Now, notice that this would be 20 cubed. I'll go ahead and write this out. This is 20 cubed. This would be 8,000. The problem was designed to have a few easy cubes in it to make the arithmetic simpler. So this is 125. Plus 64. Plus 27. Plus 2. Now you'll notice, and this was by design, this comes out to be exactly the value of the base, 8218. And so this is all equal to 8218 elevated to the 8217. Then out here, and you can verify that this sum right here is the value of the base. Okay, so that's 8218 again. $82.18. Now again, it's useful here just to look at this. This is to the first power. You have it to this power here, 8217. And so we get the remarkable 8218 raised to itself. Okay. Now I worked this problem in reverse. It was another problem that I thought of, and I decided just to do it in reverse. It seems slightly more interesting to do it this way. But what we have shown here is that 8218 raised to the 8218 is the sum of 6 cubes also. See this sum? This sum right here, this sum is the sum. That's what we're talking about, right? So we have written this object. This is the sum of 6 cubes, but it's equal to the tidy 8218 raised to the 8218. And I've seen the reverse of this problem worked at short list IMO problems, believe it or not. They would have started the problem with this, and they would say, show that this can be written or expressed as the sum of 6 perfect cubes, not necessarily distinct. Okay. But anyway, I thought it was kind of a cool problem to work in either direction. When you first look at this, you might go, what? Simplify, or where do you start? Whether, like I say, it's very simple to identify this greatest common factor. And then when you factor it out, the problem was designed where the sum of what was left is actually equal to the base, of the original exponential, which leads to this 8217 plus 1 is equal to 8218 over and over. But anyway, that is the answer, and it's related. You can do something similar to this to show that certain types of problems can be written as the sum of as many cubes as you want, the sum of many fourth powers as you want, and so on. The number has to have some structure to it for it to work out. Not any integer, but it's certain integers that are designed like this, admit this property. Okay, that's all.